Hello, I hope your test went well today, and here are the notes today on quadratics. This should be kind of a review, so I will keep a fast pace. First of all, there is 3 forms for quadratics. You have standard form. The benefit of this form is that the constant gives you the y-intercept of the quadratic function. Give me a second to screw in my pen. Thank you so much for your patience. This is the y-intercept. Next is vertex form. This gives you the x and y coordinates of the vertex. Something special to note is when you take the opposite of the x coordinate, it also becomes the axis of symmetry. Lastly, we have factored form, probably my most favorite. And these give you the 2 solutions, or the zeros. In other words, the x-intercepts of the function. So here is a sentence that I'm going to read slow and carefully that really kind of weaves those vocabulary together. So if x equals k is a solution to the equation f of x is equal to 0, then k is a 0 of the function. I want to pause right here and kind of explain why it's called a 0. Because literally it's an x value that when you plug it into a function gives you a y value of 0. It makes sense. Such that k comma 0 is an x-intercept, just a familiar ordered pair, of the function y equals f of x. Lastly, x minus k is a factor we're relating to multiplication, hence the parentheses, of f of x. So let's deal with some examples where we're going to actually write an equation here. So if we have a parabola with a vertex of -1, 5 that goes through the point 2, -13, I almost have enough information just to write a function straight off the bat in vertex form. So if we have y is equal to a times the quantity x plus 1 squared plus 5, you might notice that we have one too many variables specifically with this stretch. And we're going to solve for this last piece of information by substituting x and y from this random point. We've already incorporated the vertex into this form, so that's why we're plugging in these. The y coordinate gets substituted in for y, and the x coordinate gets subbed in for x. Now let's simplify this. Starting with parentheses, we get 3 squared, which becomes +9. We're going to isolate a by subtracting 5 to both sides, and we get -18. Lastly, 9 times what number is -18? And we know that a is equal to -2. Lastly, make sure to answer the question that is being asked. It wants us to write an equation. So we must write our final equation with our stretch of -2. One suggestion I have is that you should never leave a math problem without knowing or feeling pretty sure that you got the right answer here. One way to check that is to quickly visualize this with a graph. You'll see that the vertex is in the 2nd quadrant, and that other point is down in the 4th quadrant. And we can see that this quick visual matches the description of our function in vertex form, so we are good to move on. Let's talk about 2. Here they give us 2 zeros and a y-intercept. So instead of using vertex form, I think factored form would be the preferable option to set up our equation. Again, at the end of the day, they are all equivalent. You just have to think about which one is useful. We do not know the stretch, but we do know the 2 intercepts, which sets up our factors for our equation. Interesting thing to note here, if you can kind of visualize this multiplication, this double distribution, you'll already see that the constant is going to be +12. So I already know in my head that a is equal to 1. But just for the sake of having fun, let's substitute in x and y to verify that a is equal to 1. In other words, there are no stretch. The y-coordinate is 12. A is what we're solving for. 0 minus -2 is -2. 0 minus 6 is -6. Oh my gosh, how lovely. That simplifies to +12, which means a must be equal to 1, just as we suspected. Lastly, let's write our equation in factored form. You can use function notation for this, but I'm using y. You can put that sneaky one in or not, because it is still the same. Yay! Let's talk about vertex form. So again, this is in factor form. The fastest way I think I'm going to do this is just by multiplying these two binomials, in which case I get x squared minus 3x minus 5x plus 15, which simplifies to x squared minus 8x plus 15. From there, to get the vertex here, you are going to want to complete the square. And to do that, you're going to take this middle term b, take half of it, and square it. That becomes our special number. Negative 4 squared is positive 16. And there's a couple different ways to do complete the square of where you kind of put and take away this special number. A good mathematician is a little bit lazy, so we're trying to minimize the amount of work and steps we're going to show. So I'm going to add this 16 to the right-hand side of the equation. I know my goal is to get this in vertex form, so I'm going to subtract 16 from that same side, just to again show that I'm just not adding or taking anything away from this equation. I'm basically rewriting 0. But the benefit of this 16 is now this trinomial over here, if we factor it, we are actually going to realize that it's a perfect square trinomial such that it factors into x minus 4 squared, right? Which numbers add to negative 8 and multiply to positive 16, negative 4, negative 4. Lastly, we simplify the outside and we get negative 1. Did it ask for the vertex? Not necessarily, but it's a good thing to state. We know that our vertex is now at positive 4, negative 1. What do you notice about number 4? Why did I include this specific example on the notes? How is it different? This one is slightly different because we do have a lead coefficient of 2, which makes our completing the square a little bit more tedious, but we can still deal with this the same way. The first thing you're going to want to do, though, is separate the terms with an x from the constant. I know I'm going to add some number and take that some number away, but before I do that, I'm going to want to factor out a 2. Lucky for us, both x terms are even. And we're going to preemptively take out a 2 out of that constant as well. Same process as before, now that we have a lead coefficient of 1, half of 4 squared, 2 squared is 4. So that is the number I'm adding, but be careful about when I take this number away, because I'm not adding 4 to this equation, I'm really adding 8 because of that 2 I already factored out. So I'm going to instead take away 8 on the outside. This trinomial again factors. It is a perfect square trinomial, not by accident. That's the whole goal of completing the square. And we get the quantity of x plus 2 squared. Simplify the outside and we get minus 5. Lucky for us, we can identify the vertex here, which is at negative 2, negative 5. Again, I'm just going to quickly verify this with a graph. I know my y-intercept is 3, and I have a positive slope for my y-intercept and a stretch of 2. This is looking great to me. It makes sense. Let's talk about how to grab the vertex when something's in standard form, because completing a square can be quite tedious unless the numbers are pretty nice like this. That's why I like quadratics, because you really have to use your critical thinking skills about which method is going to be most effective here. So when in standard form, you can always use this formula to get the x-coordinate of the vertex. If you consider the opposite of b and divide it by 2a, that is going to give you the axis of symmetry. What does this notation mean? How do I get my y-coordinate? Simply said, I just substitute it into the function and get my y value. That's all. So let's actually practice this case. See, I want you to also notice that this isn't a great case to complete the square here because this middle term is odd. Like you could, but it's just going to be painful, and I don't like pain. So let's consider our formula. I'm going to take the opposite of b, so that is -3, and I'm going to divide by 2a, which simplifies to -3/4. Now I'm going to evaluate this function when x is equal to -3/4. I'm going to use function notation here. You could use y, but it's good to communicate to a reader like what you're doing. Time to simplify our fractions here. So for 1, when I know I square this fraction over here, I know it's going to be positive. And 3/4 times 3/4 is 9/16. This end up here, a positive times a negative is going to be a negative. This is 3/1, so it becomes -9/4, subtracted from 1. If you notice here, 2 and 16 share a common factor. I'm going to simplify these fractions before multiplying them together. So I get 9/8 minus 9/4 minus 1. Let's get a common denominator here. If I was thinking ahead a little bit, I would have converted to a common denominator there. Let's do that now. Double the numerator, double the denominator. I get 18/8. And putting that all together, this simplifies to -17/8, which is our vertex. I'm going to also write that in as an ordered pair, just because that's what I'm more comfortable with when we're thinking about parabolas. Aesthetics matter in math. It's how you want to represent something. This would also be fine. Yippee! Let's deal with some real life examples here. So the reason we study quadratics so heavily is one, because they're the simplest besides a linear function. And second, it's because our whole system of gravity is based off of a quadratic model. It'd be interesting to imagine what life would be like if gravity was not based off of a quadratic model, but I digress. The motion of a ball is thrown upward with an initial height of 100 feet. It's modeled by the function s of t is equal to -16t squared plus 80t plus 100. What is the maximum height of the ball? For those of you in physics, you should know that this -16 Lie coefficient means that this is an acceleration of -16 feet. I forgot the units for acceleration in this moment, but note that this is in feet and not meters. So if we're talking about the maximum height of the ball, what that is really saying is we are wanting the vertex here. Do you want to do this by completing this square? Sure, you could, but I noticed that these numbers are pretty big, so let's use a formula instead. X equals opposite of b over 2 times a. This ends up simplifying. I'm just going to save ourselves some work. I worked this out ahead of time. That's 5/2. And we are going to evaluate 5/2. If they use function notation in the question, you should probably mirror that in your work and as your final answer. Substitute, substitute. And we get a final answer of 200. Make sure to include units here because it's kind of talking about a real life context. This is 200 feet. Lastly, you should ask yourself, like, does this make sense in the context of the problem? It starts at an initial height of 100 feet and it's thrown upward, so naturally it's going to increase, doubling its height. Yeah, seems about right. Okay, let's talk about finding methods of zeros of quadratics. So there's a lot of methods, which is why quadratics are fun. First off, we have graphing. If you're given a graph, this is probably your best option to analyze this visually and find the x-intercepts by inspection. Second is by factoring, probably the fastest method. Obviously, this is going to be your best bet if an expression is factorable. Note here that this is a binomial, but we'll notice that this is a difference of squares, so it factors into x minus 2, x plus 2. Since they are conjugates, the middle x term cancels to 0. Something special here is you're asking when this function is equal to 0. You could ask for when this function, take a look over here at this graph. You could answer this question when this quadratic is equal to y equals 1, or y equals 2, or y equals negative 2. But we're going to ask where this function is equal to the y-coordinate of 0, because that gives us our zeros. Lastly, we solve this equation, emphasis on the word solve because there's an equal sign, by setting each factor equal to 0. If a product is equal to 0, that implies that either one factor is equal to 0, the second factor is equal to 0, or both are equal to 0. Hence, two possible solutions. And we get our two solutions to be positive and negative 2. Third one we kind of touched on already, but you can actually use just to solve an equation. That is completing the square. Watch me struggle to write the word completing. I'm going to abbreviate square by actually drawing a square. But the benefit of a perfect square trinomial is that you can actually, I'm going to do minus here. When you isolate this thing, you can undo the squared by taking a square root. Just one thing to keep in mind, don't forget your plus and minus, because there's two possible solutions to a quadratic. Lastly, and my personal least favorite, but honestly the most consistent, is the quadratic formula. Boo, tomato, tomato, quadratic formula. It's long, it's tedious, but it's consistent as heck. It will never do you wrong. Not only will it get the real solutions, but it will also get any imaginary solutions as well. Opposite b plus or minus square root b squared minus 4ac all over 2a. This expression under the square root has a special name. It's called the discriminant. It helps you determine what kind of solutions a quadratic is going to have. You can kind of peer into the future and see what we're going to be working with and how many zeros it's going to have. But again, it's my least favorite because it's the most tedious. Something fun to consider is there's actually a formula for solving any cubic. If you want a jump scare, Google it. So like I just talked about, the discriminant kind of tells you what kind of solutions you're going to have. Let's break this down. So b squared minus 4ac. There's kind of three cases here. One, if the discriminant is greater than 0, it has two real solutions. If it's less than 0, I should just duplicate as I'm talking this through. That's going to have two imaginary solutions. Because that number that is negative is a number that's under the square root, meaning you have an imaginary solution. Lastly, and I love it when this happens, if your discriminant, that I'm gonna duplicate right here, because I don't want to write it out another time. If it's equal to 0, that means your square root itself is all equal to 0, meaning you're adding and taking away 0, which doesn't really have an impact on the value of your quadratic formula. That means there's only going to be one real solution, one real rational solution. I added that bit about rational because we know this opposite of b over 2a is going to exist as a fraction. So let's dive into some examples here. First off, you should consider this function here in vertex form, which is going to be your most efficient method here. I noticed that perfect square, so I'm going to do this by, I don't need to complete the square, I just need to isolate the quantity that is squared. So I set my y-coordinate equal to 0. I isolate my squared quantity by adding 18 and dividing by 2. If you're okay with that, I'm just going to not show my steps and just talk it through. Now that this is isolated, I can solve by taking a square root. As I mentioned before, please remember your plus or minus. So then I get plus or minus 3 is equal to x minus 3. Solve for x by adding 3 to both sides, and we get 3 plus or minus 3 as my two solutions. The positive case yields a solution of 6, and the negative case reveals a solution of 0. Note, I completely forgot to consider the discriminant here. We're just finding the zeros. That's okay. Sometimes if you can kind of like peer in the future just by looking at the numbers, you don't need to really consider the discriminant. Here, for 8, we could go quadratic formula because I'm immediately suspicious of this lead coefficient of 3. But if I can factor, I want to factor. So let's try that. I'm considering when this y value is 0. I'm going to do this by a guess and check method. I'm going to set up my two binomials. I know my first term has to be split up in 3x and 1x so that it multiplies back to 3x squared. And then I only have so many options for my second term. It's going to be 5 and 1. It's a prime number, so there's not a lot of factors to guess or cycle through. I want you to notice that this middle term, 2x, the one we're adding to, is fairly small. So if I were to put the 1 here and the 5 here, I notice when I distribute that the 3 is going to be multiplied by the 5, and it's immediately way too big. So if I flip the order, that's likely to make more sense. The last thing I have to consider is my signs. I see that this 2x is positive. So if I make this a negative 1 and a positive 5, it's going to be minus 3 plus 5, and that works out. I kind of talked through that pretty thoroughly, but like again, factoring, the benefit of it is because it's really fast. Normally this would take me about 15-ish seconds. That's the fluency that you're aiming for here. Once we have found our two factors that work, I'm going to set them both individually equal to 0, and I get my two solutions of negative 5/3 and positive 1. Yippee! Here's where it asks us to use the discriminant to predict the number of solutions here. One thing to note when you are using the discriminant is make sure that it is in standard form, meaning that your quadratic is equal to 0. So I'm going to do that by subtracting 6x to both sides and also subtracting 3 from both sides to get the quadratic 4x squared minus 6x minus 3 is equal to 0. My a is the lead coefficient, my b is the linear term, and my c is the constant. So substituting that into the discriminant, or the part under the square root for quadratic formula, I get negative 6 squared minus 4 times negative 3. Simplifying this ends up being 36 plus 48, which then combines to 84. Okay, awesome. We have two real solutions. One other thing I would specify is, can you take the square root of 84 and get a clean integer? Is it a perfect square? No. So since this is not a perfect square, that not only means that I have two real solutions, but I also know that those two real solutions are irrational. Because thinking about the discriminant in the context of quadratic formula, that square root is not going away. It's going to be an irrational decimal. Let's move on. This one, yay, work is done for us. I already know this has one rational solution. Again, you can kind of peer into the future by considering this by factoring, but let's verify that with our discriminant. 8 squared minus 4 times 1 times c. This is 64 minus 64, which simplifies to 0. Yippee! This is one real rational solution. On a graph, what would that look like? Remember, these solutions are the x-intercepts of the graph, so this would kind of just touch and go off of the x-axis. I'm just checking if my signs are right. Yep, it's going to be to the left. It is one rational solution. This one here, we're going to have to do some work to shuffle it around to put it into standard form. And we get 3x squared minus 4x plus 5 is equal to 0. My a is 3, my b is negative 4, my c is positive 5. Discriminant, setting that up. We get this, which simplifies to 16 minus 60. And that is negative 44. Boo. Two non-real solutions. They're fake. Fun fact, the word imaginary was originally described by a mathematician who was insulting the type of numbers that were originally invented. Turns out they're very useful, but the imaginary word still stuck. Lastly, this one is already in standard form, a, b, c, and we get negative 14 squared minus 4 times 8 times 3. I always forget the 14 squared, but this is 196. This simplifies to 96. And oh my gosh, that's 100, which is a perfect square. So not only do we have two real solutions, but they are also rational. Thank goodness. And that wraps up our notes for today. Thank you for listening. I appreciate it. Your homework tonight is going to be to start worksheet 1. The submission file is open, so please submit that when you're finished. We will go over the answers next class when you have a chance to discuss with your classmates. Bye.